Person. Thank you very much for the invitation. And I'm sorry I can't be there in person, but yeah, I've got to prove Fermat's last theorem, so I've got to get my act together. Uh, so I'm not going to talk about Fermat's last theorem, well, only very briefly. But I'm going to just any good talk starts with definitions. So let me just say what we're talking about. An interactive theorem prover, that's like a programming language which can encode mathematical definitions and theorem statements. It's like Python. A variable can be a number, or a variable can be a string or whatever. But in an interactive theorem prover, a variable could be a theorem statement or a theorem proof. And there's some examples of theorem provers. And formalizing mathematics, which is what the talk's about, means writing code in one of these theorem provers, which corresponds to mathematical definitions or theorem statements and proofs. Right, so it's sort of translating mathematics from human language into a computer language. Uh, and one example of a lot of formalized mathematics is Lean's mathematics library called MATLib, which is 2 million lines of code corresponding to lots and lots of theorems and definitions, which now covers most of an undergraduate degree and also a bunch of much harder mathematics in sort of sporadic areas. If you sort of had to draw a picture of it, it would be sort of quite uneven because there are some areas of mathematics where it's far more developed than others. For example, we're still missing sort of some undergraduate level complex analysis and some undergraduate level manifold theory, but we have an absolute ton of, homological algebra and commutative algebra that go sort of way beyond a standard first graduate course. Uh, so there's an example of a large formal mathematics library. Uh, and that's Lean's sort of, I mean, in some sense, this is the jewel in Lean's crown, even though some of Lean users are not particularly fond of that. It probably is true. Um, but analogous mathematics libraries exist in many or all of the other languages. The big difference is that um, these things are typically uh, either more specialized or there's sort of less mathematics there, or they're sort of much more focused. Like Agda has a mathematics library which is sort of hugely focused on infinity groupoids. Because if you like Agda, then you like infinity groupoids, and if you like infinity groupoids, then you like Agda. So the Agda has a lot more about infinity groupoids than Lean, but it doesn't have quadratic reciprocity or something like that. Um, so I should say that I the so what's this talk going to be about? Maybe I'll tell you that before I say what I was about to say. So Mathlib was written manually by hundreds of people over the last 8.5 years, and and what the talk's about is uh, why, like because there are other ways of doing mathematics, like you can write papers and stuff. Uh, why write an undergraduate maths degree in a weird esoteric programming language? Uh, so I thought that would be an interesting thing to think about. So I said I would talk about this, and so now I've spent sort of the last few days thinking quite hard uh, about what the point of doing that was. So I'll talk about that, and I'll especially talk about my history of what the answer to that, because I've been asked, I was involved right from the beginning, and so I've been asked many times over the last 8.5 years what the point of it all is. And my answer has really changed quite a lot. Uh, so I'm sort of going to go through a history of my answer, and then I'll ask, what we should be doing if you like. Should we keep going and write 2 million more lines, or should we just let AI do it instead? Right? Because I think that's a perfectly reasonable question. So the thing I wanted to say before I get going is I I want to I'm quite happy to have this talk run in the sort of the Kantorovich, using the Kantorovich approach, which is very different to when I'm giving some fancy general audience lecture and I just want everyone to shut up because I've got this material to get through and I'll never get through it unless I'm uninterrupted. I'm completely happy to have people just yelling out and asking questions. And there might not be many questions for the first half of the talk because it's just sort of my old answers to this question. What's the point of formalizing a bunch of mathematics? But somehow the second half of the talk, sort of the post-chat GPT part, It sort of feels to me like this is sort of a dynamic and in progress, issue, and that different people might have different things to say. So if people want to just butt in and ask questions or make observations, that's absolutely fine. So I've sort of specifically not prepared an hour's worth of material to leave space for questions. So let me make that absolutely clear. Just butting in and interrupting me is absolutely fine. I won't get het up, just the opposite. Okay, so sort of prehistory is the 2010s, uh, and I was drawn to the area because I had some kind of midlife crisis. I'd spent 25 years doing Langlands, sort of the algebraic number theory side of the Langlands philosophy, sort of the mathematics of Fermat's last theorem and the stuff that came after that. But I had this sort of, in my mid 40s, I had this sort of, this major concern. The papers were getting longer and longer, and they weren't being refereed carefully, and they weren't perhaps giving complete proofs of the things they were claiming to prove. And and I think that part of the issue was that because I've talked to other mathematicians who say that part of the adventure in their part of maths is trying to work out what's true, trying to work out what they should be proving. Whereas in Langlands, I mean, there is a certain amount of that, but sort of the fundamental questions that Langlands raised in a slightly vague form uh, in the 1960s and 70s, and now we have much more precise forms of these things, they're almost certainly all correct. Whenever you sort of try and work out an example that's well beyond what mathematics is ready to prove, you try something numerically and it turns out absolutely right. So Langlands is absolutely spot on with his conjectures. And so if somebody writes a 200-page paper and it proves that, like abelian surfaces over totally real fields are potentially modular, then you're not going to find a counterexample to that statement because like abelian varieties of an arbitrary dimension over an arbitrary global field are going to be modular, right? This is a much stronger theorem is almost certainly true. And if it takes 200 pages to prove sort of an incredibly small fragment of that, which would still nonetheless be regarded as a breakthrough, you can't just spike it by saying, well, the main theorem's wrong, right? But what you can worry about, and what I got more and more worried about, was whether the proofs were complete. This was the thing I was concerned about. They might even sort of be a correct sketch, uh, but somehow the proof's definitely complete. And I'd seen explicit examples of where people were leaving gaps and were sort of saying, "Oh, well, this is all right because, somebody told me that they knew how to do it," or there's this unpublished preprint where somebody claims to have done it. Um, so I could point to sort of concrete, more and more examples in the literature where this was happening. And I was just thinking, well, it's all well and good saying that the experts know it, but like when the experts are dead, what's going to happen? Like, is it really acceptable? If we're not documenting what we're doing accurately, then is this acceptable? So this is what sort of started me worrying in 2017. And I'd read this thing in the AMS from 2008 about these theorem provers. Uh, and so I reread that journal article, and then I decided, there was a special issue of the notices about this stuff a long time ago, 2008, 2009. So I so I was started wondering whether these tools could help solve this problem that I was worried about. And then I very quickly realized that they were absolutely in no position to solve that problem at all. Uh, because even though they'd existed for a very long time, nobody had sort of done what in my mind was like the completely obvious thing to do, which was sort of make some coherent, classical mathematical degree. There was this big proof in Rock where they proved the odd order theorem and they developed a lot of undergraduate group theory and representation theory. But when you read the paper, they're really proud to, talk about the fact that how they've developed everything using constructive mathematics, and they've developed representation theory, but they haven't used the complex numbers because the complex numbers are uncountable, which is problematic. And I'm just reading this thing, thinking, this is sort of, for me as a classical mathematician, it just reads like lunacy. It's just like, what is the point of developing a constructive mathematics library if all of the mathematics departments are just arguing classically? And since then, I thought constructivism was dead, but it turns out it's alive and well. and living in computer science departments. And it's mostly computer scientists using these tools in the 2010s. So I realized very quickly, you know, I one of the beginning stories was we defined schemes, and my first question was, well, how are schemes defined in the other theorem provers? And it turned out that no one had ever defined schemes. Despite the fact that Voivodsky had been working with the software for a decade, nobody had defined schemes in any other theorem prover. So I realized very quickly that no way were we going to fix issues that I was, having with 200-page papers in the Langlands program, because we were a million miles from the Langlands program. But the other stupid thing that happened was I was also teaching our intro to proof class. Uh, so to try and learn the software, I chose a random, well, Tom Hale suggested Lean. So I spent the summer of 2017 trying to do the questions that I was going to give the undergrads at Imperial in October, trying to do these things myself in Lean. It was really, really enjoyable. Like trying to, it really changed the way I thought about a lot of the, I found errors in my problem sheets and imprecisions where, the question looked to me like it makes sense, but then when you sort of dig a bit further, you realize that it can be interpreted in more than one way. And I realized that actually this software was I found it great fun to work with basically. And so it sort of completely derailed, instead of spending evenings and weekends playing computer games, I spend evenings and weekends playing Lean. This was my new obsession, as my partner called it. As my
So,
partner called
Kevin,
it.
can I ask a
Yeah,
question
go. Yeah, yeah.
about why do you think, even when Vygotsky was involved, why didn't he think? I mean, it's hard to get into his mind, but why do you think he didn't think to try to do what Mathlib did?
He had a midlife crisis as well, and he was concerned that his theory. I was concerned that papers in my area was wrong. He was concerned that his papers were wrong, and then I think he got concerned that maybe set theory was inconsistent. And then he invented this new way of thinking about equality, and then he lost all interest in algebraic geometry. That's my guess. I mean, I never got to ask him because he died. He died the summer of 2017. Like the moment I got interested, 2 months later, he was dead. So I never got to ask him. But I think he just lost interest in algebraic geometry, and he became a constructivist. And it's incredibly difficult to do schemes constructively, because you can't prove that the topology on the spec of a ring is a topology, constructively. One of the arguments, one of the axioms for a topology needs the law of the excluded middle. So I suspect that he just got interested in other things. I think that's what happened. So in 2018, when I was using this software more and more and sort of playing with the idea of, doing harder stuff, I started to give talks about why the mathematics community should start to formalize mathematics. And my argument was incoherent. I was just super excited, but my argument was probably quite incoherent. And furthermore, it was very combative. So, for example, people would ask me what the point was, and I would ask them, well, what's the point of doing what you're doing? I mean, like it's all relative, isn't it? I mean, they make me just as, like you do Langlands. I used to do Langlands, but like, what's the point of doing Langlands, especially if you're building on things that might not be true? Uh, and 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 I would argue that doing Langlands, you might get funding, but it's not actually useful, in terms of growing the economy. So, great, it implies Fermat's last theorem, but Fermat's last theorem is somehow supremely useless, right? So this was one of the arguments I would give in 2018. And this argument did not go down well, right? This is not the kind of thing a mathematician wants to hear. Uh, the fact, what I'm doing is just as pointless as what you're doing, and so you can't ask me why I'm doing it, right? That's not a good argument, it turns out. And also because computer scientists were using the systems, I would also get gigs speaking to computer scientists, and there I was just like I was equally combative because I was just furious with these people in that they'd had 30 years to make a maths library like MathLib, a basic undergraduate maths library, and it wasn't there. Maybe the closest was sort of Isabel's archive of formal proofs, which was classical, but there's sort of like lots and lots of different definitions of a ring. And there's sort of not one definition of a ring. There's all sorts of different experiments with different definitions of rings. And people were just focused on constructivism and type theory and all sorts of other things. So I berate them, for thinking about it. It was clear that there was one important question, which is like build an undergraduate maths library, because that's how we get started. Um, and somehow they'd had 30 years to do it and had not done it. And somehow the example that I would give them was the fundamental theorem of Galois theory, which was on Frake v. Dijk's list of 100 open problem, no, 100 formalization challenges. So fundamental theorem of Galois theory, insolvability of the quintic, and impossibility of, sort of duplicating the sort of yeah, things that you would solve using Galois theory, like insolvability of the quintic. This at the time in 2017, nobody had ever formalized in any theorem prover. And somehow I could just see that formalizing, the basics of Galois theory was be a really, really nice and interesting project. And I was kind of amazed that nobody had done it. So this was my go-to example. Why has nobody done the fundamental theorem of Galois theory? Because it's such a fundamental question. And as I say, this didn't go down well either, because it turned out I didn't really understand what the important questions were for the computer science community. And so I was just sort of standing in front of them going, why are you not thinking about the obviously important question? And I think they were kind of thinking, well, actually, there's plenty more important questions as far as we're concerned. And we're not that interested in Galois theory. Uh, so I would argue to the mathematicians that, what we say, I was just concerned that we say we've done this and we say we've done that, but have we really done this? What if there's gaps in the literature, and what if people die? And then, I was particularly concerned that, maybe there were major results in the literature that weren't properly proved. We'd seen this with the classification of finite simple groups. Like mathematicians were happy to announce it in the 1980s, and then they kind of retracted it, and then they announced it again, but they still haven't written it, right? If the experts all die, it's still very difficult to find it in the literature. But they're close to finishing it, and then I'll remove that criticism. But mathematicians are not great at writing down all the details of major results in the literature sometimes. And of course, there's all, you can easily point out, there are two papers in the annals that contradict each other. There are errata for papers that were written 40 years earlier. The whole thing is very easy to poke holes in the way mathematics works. And I gave a talk like this, a combative talk saying that, maths is sort of in a mess, and here are, here's an explicit list of, here's a list of lots of things that mathematicians have done, which are sort of manifestly shouldn't really count as mathematics, or problematic from the point of view of formalization. And then a philosopher of mathematics sort of took me out to dinner afterwards, after this talk in Paris, and explained to me that actually that was the nature of mathematics. The fact that mathematics is like this, it's sort of full of chaos, as I was calling it at the time, because it's done by humans. This was the main argument. Like, when it's the sort of modern research, there's inevitably noise and errors and chaos. And then people understand it and generalize it and simplify it and conceptualize it and find the right abstractions. And then by the end of it, everything is completely trivial, and we teach it to the undergraduates. This is what this philosopher of mathematics told me. And he gave the example of sort of the work of Cauchy on real analysis, when people were just sort of trying to work out, Newton had been around for ages, but somehow we were trying to work out what things like dx actually meant, and rigorous notions of the real numbers and continuity and differentiability. And Cauchy's work has errors and omissions and things like this, but somehow it was eventually understood correctly, and now we teach it to the first years. And I kind of went away from this philosophy department kind of realizing that actually that was probably a completely valid reason for why there's chaos at the boundary, and perhaps I should stop attacking the boundary, because maybe it was just an inevitable part of humans doing mathematics. But actually, I realized later that it doesn't always work like that. And global class field theory, the main theorems of global class field theory were proved over 100 years ago, the beginning of the 20th century. We had some really profound theorems about Galois groups of number fields. When is the Galois group of an extension of number fields abelian, and can we somehow, quotes, classify all the abelian extensions of number fields? And this has been generalized and conceptualized and simplified, and abstractions have been discovered, such as group cohomology, that makes everything much easier. But it's still the case that the main theorems of global class field theory, it still takes a book to prove them. So, and that's mathematics, which was sort of fully understood 100 years ago. Well, I guess 100 years ago, there was still a bit of noise, right? But now there's no noise. There's precise statements and proofs. And the proofs are still very difficult, right? So things do get generalized and simplified, but eventually they might not become trivial. Maths is hard. Uh, so that philosopher was not 100% correct. Uh, so anyway, academics were skeptical, um, but the undergraduates were far more pliable, it turned out. And I was teaching them this intro to proof class, uh, and it turned out that some of them were very interested in formalizing mathematics. And so I started a lean club at my university, and I had first year students learning Galois theory because I told them they should prove the fundamental theorem. I'd taught Galois theory the year before, so I gave them my notes and told them to go and prove the fundamental theorem, by just typing the notes into lean. And this turned into a paper that was published in Experimental Mathematics, with me and a bunch of undergraduates. It was great to write a paper with undergraduates about formalizing schemes. And one of the people involved became a maintainer of Lean's maths library. And then another one won the best first year project prize. So the undergraduates were getting some mileage out of this idea, even though the staff were thinking I was a crackpot. And the staff would raise issues. It's like, these students are coming to my lean club and stay till 1 o'clock in the morning on a Thursday night. And was I distracting them from their coursework? But both of these two students I'm mentioning here went on to get PhD offers, and now they're both working for tech companies doing lean as their day jobs. So for those people, it worked out really well. And then, of course, things moved on. And by 2019, I'd stopped trying to, drive attention to the area by being intentionally provocative, because we'd done a much better publicity stunt, which was formalized the definition of a perfectoid space. And the area got some momentum as a consequence of that. More mathematicians moved into the area. And so I realized I needed a better answer to, it's no more pointless than what you're doing. And at least we know it's right. Uh, and and indeed, I'd sort of come by this stage. I was completely convinced that the software could handle perfectoid spaces, so it can handle anything, right? That was sort of I was convinced by 2019. All mathematics could be done in theory in software like this, and so kind of thought, if we can do perfectoid spaces, we can do anything. And so this is a new way of doing mathematics. This surely is going to revolutionize mathematics somehow. But I couldn't really explain how that was going to happen. My argument was sort of slightly vacuous, really. Uh, you know, I this is what I became, I came up with this idea that, like, if we were digitizing mathematics, right? And digitizing mathematics was bringing it into the 21st century, right? That was the selling point at this point. And I said, we digitized music and we got the CD, and the CD was kind of crap because it would, like, you'd scratch it and it wouldn't work anymore and it would jump in weird ways. And CDs were fiddly and annoying, and the artwork wasn't as good as vinyl. And like, CDs were not the great selling point for digitizing music. But then Spotify and other things come along, and Spotify completely turned the music industry on its head, right? It was, now is, now lots of people have Spotify, and that's the way I consume essentially all my music now. And I've got 200 pieces of vinyl, literally 6 feet to the left of me over there, that just sit in my office and never get listened to because I don't even have a record player anymore. And if I want to listen to one of those pieces of vinyl, I just find it on Spotify. So I argued that, digitization of mathematics was just the same, right? Well, I don't quite know why we're doing it, but the answer's coming, and the answer will turn mathematics on its head, right? That was the idea. Digitizing mathematics, it makes it more flexible. We could use it in new ways. Computers can think about it. It's like it's a new idea, and I don't quite know where it's going, but we should do it, right? And people did buy into this argument that it was clearly a new way of doing mathematics, but I was never particularly clear on exactly how it was going to change, change mathematics. Uh, but I was also very, very enthusiastic, and I've got very nice trousers, and so people sort of, just bought just sort of bought the package. Then in 2020, there was this thing, right? There was this liquid tensor experiment. Peter Scholze proposed a challenge to formalize the proof of a theorem which he had in his work with Scholze, in his work with Dustin Clausen Scholze. And he was complaining that he sort of couldn't keep all the proof in his head. And he was also complaining that nobody else had read it. Uh, but I could see that this was a golden opportunity. Let's prove that we can do recent work that a Fields medalist has done and is complaining that it's sort of too conceptually messy as a proof for him to actually understand. And I was like convinced that a computer would be able to understand this argument. So he challenged the entire formalization community, and the only community that did anything about it was the lean community. Right? All the other theorem provers, they were just like not interested in that question, more interested in type theory, more interested in constructive mathematics, more interested in computer-assisted proofs. And that was what hammered home to me the fact that I really shouldn't have been berating the other communities because they're just not interested in research. I was trying to convince somebody that worked in AGDA that they should be interested in the Langlands program. And after a lot of sort of backtracking and interaction, I realized that they weren't interested in group theory, right? They already thought that a group was a pathological object because it wasn't an infinity groupoid. And so I thought if I can't sell them group theory, then I can't sell them because the Langlands program was all about representations of one group and representations of another group mysteriously being equal. But if they're not interested in group theory, then they're obviously not going to be interested in what Scholz is doing. And so I sort of did a lot of backtracking and apologizing. Um, but for me, this was a great project, you know, trying to prove a theorem of Clausen and Scholze. So this was the opportunity. And 6 months later, it had been done. So, look, people in the community came together and formalized this argument, and gave a fully verified proof in lean. And Scholze was massively excited, wrote this very enthusiastic blog post. And next thing I know, Nature's on the phone asking what's going on. And I could point them to Scholze, who had written, this quote, I find it absolutely insane that interactive proof assistants are now at the level that within a very reasonable time span, they can formally verify difficult original research. This was he said, a Fields medalist said this, and it was his own research. And all of a sudden, you can kind of see that, maybe this is justification. Uh, so that was sort of 2021. Um, and as I say, we got some, added respectability. And also, of course, we could point to other things the formalization had done. We'd simplified the proof. The original paper proof that Clausen and Scholze had written used stable homotopy groups of spheres. And we kept putting that off. We didn't fancy formalizing that because that was going to be a massive detour. But the formalization gave us precisely the statements uh, which they needed from this theory. And then we sort of looked at those statements and thought, well, can we actually get these statements without formalizing the entire theory of, fundamental groups of spheres? And we realized that we could. And we found a much simpler proof of the statements that were needed for the liquid tensor work. And as a result, we removed the dependence of the argument on stable homotopy groups of spheres. And Masso, one of the co-authors of the Perfectoid project, wrote this document, Why Formalize, in 2021. And he gives lots and lots of, because he's much more sensible than me. I just open my mouth and say whatever stupid thing comes out. But he sort of is a more mature person. He sort of thinks, he gave a very coherent, well-reasoned argument that, formalization offers new ways of explaining mathematics, new ways of teaching mathematics, driving us to the right abstractions, the right way of thinking about mathematics. But one thing he stresses in the introduction to this 2021 note was that the idea AI is not coming from mathematicians, and the point is not to replace them. And indeed, AI doing mathematics in Lean is a complete fantasy. Don't worry, he says, we're not after you. So that was 2021, and that's the first half of my talk. That's sort of historical background. And then, of course, the next thing that happens in 2022 is that ChatGPT appears, and all of a sudden, this idea that computers might be doing mathematics instead of humans is suddenly, in our face, right? In 2023, language models were writing Python code, and at this point, I was just like, great, they've figured out how to write Python code because there's a billion lines of Python code on the internet, but there's like 1.5 million lines of lean code on the internet. So we're in big trouble, right? We can't get these things to write lean code because there's not enough lean code to train on. So I like immediately the main question is how are we going to multiply the size of MathLib by 100? All right, how are we going to make it 100 times more efficient? And I really had no answer to how this was going to happen. But it turned out that was the wrong question because in 2024, somehow using reinforcement learning, DeepMind had a tool which could write lean code anyway. And it sort of solved three of the 2024 IMO problems in very, very poorly written lean, which did compile. Like one of the proofs started was let's do induction on 10, like for no obvious reason. And like your first reaction to that question is, what does it even mean to do induction on 10? But in lean, you absolutely can do induction on 10. And and yeah. And that was the first line of its proof. If anybody's interested later on, I can tell them what it means to to do induction on 10. Um, but DeepMind's tool has really, presumably it trained on MATLib, but it was certainly relying on MATLib. It was importing theorems from MATLib to answer these IMO problems. And so now all of a sudden, there's a very good answer to why make MATLib. It's like because AI tools can now do very, very hard undergraduate level problems, and without MATLib, that wouldn't have been the case. Uh, so in 2025, so now we're sort of up to basically the present day, and that's where I'm going to go for the rest of the talk. In 2025, we have this tool called Aristotle, written by Harmonic, and they made it publicly available. And so you can ask, you can type in Aristotle will write lean code, but you can ask it questions in natural language, or you can ask it a lean question and give a proof in natural language, or you can ask it a lean question and not give it any proof at all, just ask it to prove it, and it will output lean code, which attempts to solve your problem. And there's this startup Math Inc. and they have a tool called Gauss, uh, which finished a lot of proofs in the prime number theorem plus project. And I don't know if Alex has got anything to say about that. Was that a step in the right direction, or was that actually a useful contribution? If Alex
Uh,
there,
yeah, it's going to require a lot of refactoring, but I mean, it depends on what quality code you want. If you want MATLAB quality code, then there's a
yeah.
lot of things to do. If you just want the proof solved, which is all we at the time wanted, they absolutely finished the project.
Right. So this is something I'm going to get onto later. Uh, what, is like this question, like, what's the point of why formalize mathematics? It can sort of mean more than one thing. It can mean write sort of beautiful code, or it can mean write really crappy AI generated code. And that's sort of, there's two different questions there. So we got sort of possibly not MATLAB standard AI generated code that proved a lot of theorems and helped Alex along his way. Uh, and then 2025 IMO, suddenly there's four companies claiming gold medal, two writing natural language proofs and two writing lean code. And now we've got the 2025 Putnam. And again, we've got two tech companies claiming full marks on the 2025 Putnam, autonomously solving the problems uh, and getting full marks. But of course, this is undergraduate level mathematics. But then there are these Erdős problems, some of which are very hard, not all of which are very hard, right? Erdős problems are interesting because some of them are very profound and difficult, but some of them it turns out that they were easy and people didn't really think about them. But it turns out that maybe some of them were easy, and then maybe an AI can do something, or maybe an AI can write lean code that does something. But I just say Erdős problems because it sort of sounds a lot sexier than the IMO and like the IMO and the Putnam are sort of, for undergrads, whereas Erdős problems are sort of for everybody, right? They're for researchers. So that was what happened last year. And as I say, that a lot of things happened. This area is sort of moving really, really quickly. Uh, so it was a bit chaotic. And so how I want to finish this talk is sort of, now we can ask the question again, right? After this whirlwind year, we can ask the question again, why formalize? And taking these things into account. And I think the answer changes hugely. Uh, the first question we could ask is, what exactly do I like? What mathematics am I talking about? Like, am I saying why formalize undergraduate mathematics or why formalize research mathematics? Right, that's two different questions now. We're now at the point where we can like take those questions apart, and those might have different answers. And I think the answer to why formalize undergraduate level mathematics is, well, that's what they needed, right? That's what these tech companies needed to solve IMO and Putnam problems. Right now, nobody's asking that anymore. Nobody's asking what's the point of MathLib. MathLib has got funding coming into it because people have realised that it's really important to like keep MathLib alive, let it grow, make it better. Now nobody is asking what the point of MathLib is. People are just like, isn't it great that we've got MathLib? It enabled AI to formalize Putnam problems autonomously. So and that is surely some kind of progress. But what about the other question? What about formalizing hard modern mathematics, which is something that, yeah, that was a dream for me in 2017. But actually, I'm involved. I'm involved in two projects, to do with formalizing hard modern mathematics. You see, you don't need that to solve Putnam problems, right? So let me just say briefly these two projects I'm involved with. The first one is formalizing. I'm beginning the very, very long journey towards a fully formalized proof of Fermat's last theorem. Uh, and right now, what I'm doing is I'm trying to prove Fermat's last theorem modulo the 1980s. And because I proposed this in 2023 when AI wasn't anywhere near as good, and I thought that this project I could sort of envisage this project even with 2023 tools being sort of doable in a 5-year time span. And I said I'd have it done in 5 years. So if I assume everything done in the 1980s, so that's basically formalize a 100-page paper. That's somehow a sort of a slightly vague way of summarizing what the job is. Summarize a 100-page paper, but assume all the references. And the justification I gave when I was proposing it was obviously another publicity stunt, because Fermat's last theorem is sort of a big theorem. Uh, but another question you can say, well, is the proof actually right? I claim that these Langlands people are a bit vague now, but I claim that Langlands has gone off the rails a bit, but had it gone off the rails in 1994? There's a question. Is the proof actually right? And of course, I absolutely believe it's right. But something did happen. It's like, we found a paper from the 1950s that was doing calculations with divided powers that were needed for Grothendieck's foundational work, with Berthelot on crystalline cohomology. Like the theory of crystalline cohomology had a gap for 20 years that nobody ever noticed because it was in the middle of a proof of a technical paper whose main theorems were all correct, right? But there's an incorrect proof, with not an obvious fix in the middle of some technical lemma that may or may not be correct. And for 20 years this nobody noticed this. And then 20 years later somebody came up with another proof. So there's no longer a gap. But actually crystalline cohomology was broken for the first 20 years of its existence, or the first 15 years. And nobody noticed that. And it was sort of events like that. And I was going to use crystalline cohomology in my proof. And when I heard about the gap, I rerouted, and now I'm going to use finite flat group schemes instead. But so that's another, one could, well, it's still an open question, right? Is the proof correct? I mean, it's bound to be correct. It's bound to be both complete and correct, but let's just check. But the main argument for the FLT project, I think, is look at what's happening with Erdős problems. right? Look at what's happening with Erdős problems. AI is doing Erdős problems, and AI is writing lean code that does Erdős problems. But the thing is, I'm not particularly interested in these problems. I'm interested in the Langlands program, and I want to see AI solving problems in the Langlands program. And the necessary prerequisite for AI solving problems in the Langlands program in Lean is that we can actually state these problems unambiguously and correctly in Lean, right? And the thing is, I don't trust AI. I don't trust today's AI to be stating hard problems in modern number theory. I don't trust AI to be writing down the definition of a cuspidal automorphic representation. Okay, I might be paranoid or pessimistic, but I don't trust AI to do that, right? Because Lean can check your proofs, but it can't check your definitions. You forget one of the axioms of an automorphic form, and Lean isn't going to say this definition is wrong. Lean's going to say what you've written here is mathematically valid definition of something, right? It's not going to say it's wrong. It's going to say yes, this compiles, but it is going to be wrong. So how do we get AI doing Langlands? Well, unfortunately, here's some buzzwords that I just sort of wrote down in like 2 minutes flat, just sort of thinking about many of the things that we need, which go into the proof of Fermat's last theorem, or which go into the proofs of modern results in the Langlands philosophy. And these are just very, very difficult mathematical objects, which we could do, but we haven't done yet, right? They're not in MATLib yet. MATLib has a lot of stuff, but it really doesn't have much of this stuff. Okay. So there's a bunch of very, very difficult definitions. So now, like, and the problem is I just can't get the world to stop what they're doing and make these definitions in Lean, right? That's what I want to happen. But people want to prove theorems, they don't want to make definitions. So I argued that actually, if we've got motivation to make the definitions, let make this definition because we need it to prove Fermat's last theorem, you kind of feel that, like, there's a justification to make these definitions. So let's try and prove Fermat's last theorem. Oh, look, we've got to make all these definitions. Ah, but that's going to make the library better. Oh, look, we can suddenly state lots and lots of deep and profound conjectures. I argued that that was sort of a big step in the right direction. Uh, yeah, I'm allowed to skip proofs, but I said I wouldn't skip definitions, you see. So there's some things that we're going to have to be doing in the next few years. Although I don't need all of these things because I'm going to skip the 1980s, so I can skip a lot of this stuff. But I'm certainly going to need p-adic Galois representations. That's for sure.
Can I ask a question?
Yeah, go.
On the previous slide, the discussion of you wouldn't trust AI to write your definitions. I don't know if you saw about my discussion with Christian Szegedy about definitions and his opinion on these things.
Oh, Szegedy is going to say I'm naive and it's all fine, right?
Well, no, not that it's going to get it right the first time,
Oh,
but that just in the same way as math is chaotic and eventually fixes itself, as AI generates more and more theorems from those definitions, it'll realize that the theorems are wrong if the definitions are not right.
yeah.
It's like mathematicians constantly refactor what they're doing. The AI should also have a refactor tool. What do you think of that idea? I'm curious.
Yeah, I think that this sounds great in theory. And now let's do it. Let's do some tests in practice. I think that would be a very interesting test to do in practice. Uh, but yeah, in theory, maybe. We shall see. Yeah. Maybe I'm being paranoid. See, this is why I'm sort of, yeah. I might be. I think mathematicians tend to be sort of cautious. So yeah, maybe I'm being overcautious. So the second project I just wanted to flag is this. I have an annals project. So I thought that this Fermat's last theorem project would enable us to start stating, modern theorems and conjectures in Langlands. But then I'm kind of thinking, why limit myself to Langlands? I spent the last 5 years sort of talking to mathematicians, in all different areas of pure mathematics. So maybe we should be thinking about formalizing statements of what's going on at the boundary of mathematics in all areas of mathematics. And I got money to fund 4 postdocs who are now formalizing statements. Currently, we're just doing Annals of Mathematics from 2020 and beyond, right? We're going through all the papers, and for each paper, we're saying, can we state this theorem? Can we state the main theorem, like one of the main theorems? And if we can't state it, we're making definitions until we can. So again, it's driving definitions forward. It's humans making definitions, and it's pushing MathLib in directions which are relevant to modern research, which in my mind is the important directions to be going in. MathLib kind of sort of grows organically, right? There's no the maintainers cannot write a manifesto. The maintainers cannot write, we think MathLib should be going in this direction, this direction, this direction, and we will prioritize, contributions in these areas. And we're not interested in that direction, that direction, and that direction. And if you're interested in those, then make your own repo, right? The MathLib maintainers cannot write that document because the 30 maintainers have got 30 different opinions as to what's important. And so instead of trying to push the maintainers around to my line of thinking, I'm going to do this instead. I'm going to try and formalize statements of what's been happening in the annals recently. And if we do most of the annals, we'll start on some other journal, JAMS or whatever, Inventiones, or we'll start going back to 2015 or something. But there's plenty of difficult modern theorems out there, and I think that any self-respecting maths library should at least be able to state them all. It might not need to have proofs of them all, but it should be able to state them all.
So you have in mind to actually PR all this to MATLib or have the analyst
Well,
project
we're
standalone?
not going to PR the statements of the theorems, and of course, the statements are all solid, right? But when definitions show up that should be in MathLib, we have a discussion. Does MathLib want this definition? We've got a prototype version, things like this. Like we had a definition of a Jordan curve. There's no Jordan curve in MathLib. And then Gueza was like, we don't want a definition of Jordan curve in MathLib for the following coherent reasons. And I thought, well, that's a coherent reason. The point is we can say what a Jordan curve is in one line. So why bother saying what a Jordan curve is? And I thought, yeah, fair enough.
If you're
Jordan curve,
formalizing,
is a
if you're
Jordan curve a subset of R squared or the complexes or an arbitrary manifold? We had a definition of Jordan curve, and then one of these postdocs pointed out that our definition of Jordan curve would work for R cubed, and a Jordan curve in R cubed is just a knot. So like we defined a knot and a Jordan curve at the same time, and you're just kind of like, oh, that's kind of crazy because they were in sort of two different boxes for me, but but they're both one line long, right? And so the argument was we shouldn't have them. You have to say because some people only work with smooth Jordan curves and blah blah blah. Sorry, what were you saying?
so just a quick question. If you're formalizing just the statements of the theorems, not the proofs,
Yeah.
how do you know that the statements are correct, that you're not missing little bits that are actually...
Yeah, we totally don't know that, but we're reviewing really, really carefully. We have 3-hour meetings every week, and in those 3-hour meetings, we really heavily discuss one submit. Like we typically get merged two or three PRs only in those meetings, and like an hour will be spent proving basic theorems about the definitions we've made, and then throwing them away or putting them in a test file or whatever. We experiment, but we don't know. And we're not running any of them through AI, right? We could just take them, run it through an AI, but like in a year's time, we're going to launch, right? We're going to say, here's some really hard problems. And we feel that if we've shown them some of the AIs already, then those AIs would have a head start. So yeah, it's just manual review so far. And I agree it could be error prone. But when we go live, we're then going to have challenges. And it will be interesting to see like within a week, if AIs are going, well, that theorem's wrong, like because all the variables can be zero, right? That's exactly the kind of thing that we're super, super careful about. If ever there's a subtraction, is that a valid subtraction? If ever there's a division, is it definitely not dividing by zero? Yeah, but that's what we'll end up with when we go live in about a year's time. We'll be like, here's the lean statement, here's the paper on the internet. Now go formalize the paper. So auto formalization at high level. And AI right now can't do it, but AI might be able to do it soon, right? It's a darn sight easier than AI, please go prove the Riemann hypothesis in lean, right? Which is still science fiction. But AI, go and formalize the proof of this annals paper. That sort of might be viable in a year or so. So it'll be interesting to, I'm hoping we're going to make a really hard data set, but we shall see. Now, my conjecture is that nobody will be able to do anything for a very long time, but we'll see. So yeah, last one slide. I'll say something about the future. MATLib is currently moving very fast, being developed by lots of people, but it's got incredibly high standards for code quality. And AI written lean is nowhere near these standards. This is what Alex was saying, a few minutes ago with regard to the code that AI wrote for him. And so, thought experiment, what would happen if we just dropped all the standards and just started letting AI develop MATLib by itself? I've just asked a question on the lean zip for those of you on the lean zip. I just asked a question in Hash General called sloplib, which is like sloplib is like mathlib, but we instantly drop all standards. And instead of developing the theory of elliptic curves, we could just feed basic text on elliptic curves to an AI and say translate them all into lean. And my guess is that it will collapse. But I might be wrong. My guess is that if we start letting it write unidiomatic, crappy, poorly written code, my guess is that it will collapse, right? Because I suspect that part of the reason that MATLAB has been so successful, 2 billion lines, compiles in 10 minutes, lots of people using it, I think has been its meticulous attempts to really try and be absolutely high quality code. It's sort of, we've got fast proofs, we've got readable proofs, and more importantly, we've got maintainable proofs. As the language changes, the thing doesn't collapse. So we could sacrifice them for quicker growth. And it turns out that there are tech companies that are capable of writing many, many thousands of lines of code very, very quickly. But my instinct is that AI code is very inefficient, and it also writes the wrong lemmas and it does sort of the wrong things. So right now, I think that we're right to continue on this sort of high bar, mostly human written thing, but AI is going to get better, right? And as AI gets better, I think that we're going to start asking the question: should it just be human only Lean's maths library? Am I being overcautious? Will I be being overcautious in the future? So I'll stop there. Thanks for listening. Oh no, I won't. I've got one more page.
Oh, Kevin, before you go on to your next,
Yeah. Sorry, I thought that was the. Then maybe I'll stop.
I just want. I mean, there's a place in between, right? I mean, if you look at something like Python or MATLAB, right? I mean, there are cores to the code, and then there's all sorts of packages, right? That range from packages that are very carefully developed to packages that are almost one-offs, right? And that seems to me to be extremely useful because there's a small group that's working on a certain type of problem, and so there's some Python code that handles it. It's probably not been written. It's probably been written maybe by an applied mathematician as opposed to a computer scientist, and so it's inefficient code, but it's not slop code, right? It's not
This
AI
is
generated.
interesting. Yeah, I think this would be a very interesting development if AI companies started. Yeah, I think this might be an interesting way forward. Things that depend on MATLib but not in MATLib, and they're saying this is the theory of the take curve, written by AI, use at your own risk, could
Right,
break.
not even written by AI, written by a group of mathematicians, right? Who,
Yeah, okay, written by anything.
yes, yes,
Yeah. But sort of satellite.
yes.
Yeah. Yeah. And I guess that's sort of, I mean, maybe Alex's prime number project is that. Maybe we should just have many, many more of them. So,
And
some
then,
AI.
and this is back, I think, to what Alex was saying earlier. Some of those ideas, um, I'm looking for the right word. I'm kind of thinking of them as um, flows. Here's the basic idea, and here's the math that comes out of it. Some might turn out to be much more popular than others, and maybe that is an indication of how MATLib should redesign the fundamental architecture, right? That you have the ability to experiment on, what are, as you were saying on the Jordan curve, right? I mean, what is the fundamental ideas? What's the tree of fundamental ideas that should be developed there, right? Well, okay, you and your postdocs are working very hard to figure that out. But you do come from a certain perspective, and maybe from another perspective, in the long run, it would turn out to be better, right? Well, if we had all these satellite codes, as you called them, might see which kinds of satellite codes got picked up by broader and broader communities. And that might have an impact then on how MATLib should organize um, its development of mathematics.
Yeah. Maybe this will be what happens. So I'm not going to say anymore. I've said everything I need to say. So whatever's on the next two slides is just waffle. It's just probably a summary of the talk, but I think, yeah.
First,
Thank you very much.
thanks. And then, so can I ask, like, I keep thinking, okay, there's this thing that I do that AI doesn't do. For example, if I can try to get my code into MATLib, then I'm going to refactor it and I'm going to develop it and clean it. And then I think any of those things that I'm doing is a thing that an AI could be given.
Yeah,
Different
like AI could maybe tidy up your code.
Right. So
I
there
don't
could
see
be
any
like
reason why not.
and then you could have the golf AI go through and refactor and tidy everything up, and then suggest a PR from Sloplib into Matlib.
Yeah. I think that maybe I think a lot of people are very quick to dismiss this idea, but I do wonder, auto formalization is being solved, right? And I do wonder whether, but we can't sort of work out how to fit it all together. And I do wonder whether we should embrace it. It's going to make some people quite cross, though, of course, because there are MATLib maintainers who are like vehemently anti all forms of AI, full stop. And so
The other thing I want to ask is, Matlib is kind of like a math journal. And so if there's only one math journal that determines what is or isn't mathematical truth, that's not so healthy for the ecosystem of mathematics.
Yeah.
And in a sense, our number theory project is a kind of number theory centered sloplib, if you like, where we're allowing.
I wouldn't call it slop, but yeah, but I take your point. It's not the same quality. But I mean, the FLT project isn't the same quality either.
Yeah. I mean, from the beginning, we were accepting, before AI, we were just accepting human contributed code where the only question was, does it compile? If it does, then great, we took it.
Yeah.
And just tried to race ahead to the proof. Of course, now we've taken on so much technical debt, it's going to be an extremely laborious project to get anything into MATLAB quality code.
But what's happening? Are you finding it difficult to bump? Can you bump your code?
Bump is no problem. We are able to bump, and every so often Ruben steps in and bumps it up, and Pietro has bumped us to the architect from the original blueprint. So we're having no problem staying with changes to MATLAB.
Oh, that's great to hear, because that was one of my fears, is that you just accept any old crap and then it breaks and you have no idea how to fix it.
It's always a project, a little bit of a project to bump, but so far we've been bumping every single time we do MATLAB comes out, we bump it. It's there.
It's not really any old crap either, right? A lot of the code was written by MATLAB at the end of the day.
Yes, but now especially we're getting, if you look at the contributions, even labeling contributions by AI contributions versus human contributions, and saying this was by Claude, this is by Gemini, this is by Aristotle, this is by Alpha Proof, and we're also labeling what were the misformalizations, and you will see, about half of the statements were not formalized correctly by human experts the first time around. Missing one of these division by zero, subtraction.
I should say that I talked to the formal conjectures people, the Google DeepMind repo, and they said about 20% of their statements were formalized incorrectly. I mean, this really fills me with fear with this Annals project, because we're keeping it quiet. And then we're going to go live and there's going to be hundreds of questions, and immediately someone's going to go, well, that one's wrong.
Right, you give these statements to Aristotle, and Aristotle comes back with disproofs for 30 years.
Yeah. So I think maybe what we're going to do, so just before we're ready to release, we might we might hammer some AIs with like, what do you think of these? Tell me which ones are wrong. But we're not doing it yet. So did you merge the PR that was written by Gauss?
we didn't just upstream it directly. One of my students is actually upstreaming it in a way because the problem with the Gauss PR is that basically all the hard work in formalization, as you know very well, is if you have a natural language proof and you're trying to translate it yourself, you're like, okay, what's the theorem in the library that does this? And you go into MATLAB docs and you look it up and you figure out how to do it. Basically, the Gauss project did that, except the way that they did it is if there was some simple lemma in natural language that Gauss wasn't able to close, the mathematician there, Darren, would write a separate little lemma, or maybe the AI would write a separate little lemma in natural language in the blueprint that would basically prompt the AI to go and do that MATLAB docs lookup.
Yeah.
And so it's almost the same project. It's just it's all taking place on the natural language side, never explicitly a human going into MATLAB docs and looking for the theorem. So there are statements like, the exponential function is a map from the complex numbers to the complex numbers, and the proof is x. The x function exists in MATLAB. This. So one of my students is sort of cleaning up that aspect of Gauss, and we're upstreaming it's sort of deslopification of one order from Gauss to PNT, which will require another round of deslopification if we ever manage to get it into MATLAB. But I'm sort of not even motivated to put in the hard work to do that deslopification because I feel like in 6 months there will be systems that do it for me. And
Auto deslopifiers.
Yeah, deslopifiers.
I think you might be right. And I think this does raise questions then, like, what's the point of humans doing it at all?
Well, that was going to be my next question. Yeah, because the Gowers, the thing that I like to point to what Tim wrote in a quarter century ago about what will happen in the age of AI is there'll be this golden era where it helps us. And maybe we're in that era now. And then what?
We're quite there yet, but we might be going towards it, perhaps quicker than some people realize.
Yeah. And so what do you think? Once they can do all of this, then what do we do?
Yeah, I don't know. Should be, I mean, yeah, it should be. People are saying things. You see, I'm slightly worried that, this philosopher said this thing and it sort of shut me up. And I was just like, oh yeah, you're right. I shouldn't be, maths is, there's lots of areas in the literature that's because that's normal. And I'm just wondering if you'll sort of say, oh, you shouldn't formalize because all these things are going to happen and it's going to be fine. But maybe I'll go away and 2 days later we'll realize that you've conned me. But yeah, I mean, maybe there's a coherent argument. I saw David Silver last Thursday, who's just resigned from Google DeepMind and is starting his own startup. He was head of reinforcement learning and he was behind this IMO Silver thing in 2024. And I said to him, should we even be teaching our undergraduates lean if AI is going to write it all? And he said that his vision of the future and what's happening now is that there's a lot of sort of human AI collaboration happening right now. And he still argued it was very important for humans to be learning lean because sort of the best tools were the ones where humans and AI are working together rather than us just trying to get the AI to do all the work. And I thought that was sort of an interesting observation, especially given that we have a lean course at Imperial that's running right now. And 42 people are coming. It's the most well attended yet. And so, I was just thinking, what's the point of it? Do we just wait until AI can do it and then just call it a day?
But
David Silver says keep going, so okay, I'll keep going.
But let me give another perspective on that, right? I mean, why do we still teach multiplication tables?
Yeah, I don't know.
And
I asked many primary school teachers this question. I haven't got a coherent answer. Do you have a coherent answer?
I would say that, it's whether in the future we should still be teaching students lean is a question. I kind of think of it as assembly language for mathematics, and what we really want are higher level languages that will allow it to go back and work with the assembly language. So, but the point is that there is at some point you need to have interaction with what you're trying to do, right? And at the moment, I think the only coherent level of interaction with what's being done rigorously as a mathematician, not as a computer scientist, would be lean, right? And so that's why I think we should be training students at the moment, which obviously we aren't, except in special cases, to interact with lean, right? Because, well, there's nothing else that's coherent at the moment. Whether that should be done in 10 years after we have higher level math languages, I'm not so sure. But this ability to interact with formal proofs is going to become more and more important. And so there has to be a baseline. And at the moment, lean seems to be the the baseline that's evolved.
If I can jump in, I would say that the reason we have to teach kids multiplication tables is the same reason we want to teach kids to do a push-up. Like, you're not doing push-ups because you think you're going to be pushing heavy things when you're older, right? We have machines that do all physical movement for us, and maybe in the future we'll have exoskeletons that are stronger and faster and whatnot. No, you still want to be able to move your body. And the reason you teach multiplication tables is because that's a pretty good way to get your brain to move. And you still want to learn lean and mathematics because that's what helps your brain think. It's as good a method to help you think. And why do you want to be able to think? Well, because you want to be able to make good decisions in your life. And, I don't like.
Yeah, I don't think you have to justify why humans have to learn to think. I think there's I'm very pleased. I think it's a very coherent answer. Thank you. I can see why they got you involved in this MoMath thing. It's a, it's a very coherent answer.
It's just what we want to be doing as human beings, regardless of whether machines can do it for us. We still want to be able to think, and we want to be able to walk, and we want to be able to do a push-up.
Yeah. So another question I asked David Silver was that something I didn't really talk about, but I'll talk about now. It's that AI, it's all very well AI doing Erdős problems that turn out to be easy, or Putnam problems, like undergrad stuff. Is it really clear that these things are going to scale and AI is going to be solving the Riemann hypothesis, right? And for me, that's not clear at all, because what I worry about is that AI trains on, AI trains on what we know. And and so when you're in distribution, that's sort of fine. But when you go out of distribution by trying to prove the Riemann hypothesis, like who knows if performance is going to fall off a cliff or not? And he said that it, he thought that sort of developments were sort of taking place. Somebody would have an idea and then things would go up. Then someone would have another idea, then things would go up again. And someone would have another great idea and things would go up again. And he says that's what's going to keep happening. People are going to, because humans are going to keep having great insights and things are going to get better. And he can't really see it stopping. Because that's another question I'm very unclear on. Is AI just sort of going to peter out at some point? And it will just, maybe we'll be able to use it to review papers. That'll be good. But maybe it's sort of new proofs are going to be, ropey and lousy. But he thinks it's just going to keep getting better and better and better because humans are going to keep having good ideas about how to make it better. And that's again another open problem that, some people are very skeptical about. Some people are just like, oh, it's not going to get any better. The bubble's going to burst and the market's going to crash and all these companies are going to disappear.
But isn't that the argument? If we stop teaching multiplication tables, which I'm using as a placeholder for all sorts of things, then humans are going to stop having the great ideas that are going to make the AI keep going up and up. And we can't put the cart before the horse. Until we have an AI system that can do the math for us, we still have to do the math.
Well, some people have already chosen to stop teaching multiplication tables and others haven't. And we're seeing the consequences of those decisions.
Let me come at it from a different perspective because, most of my life has involved learning some mathematics, maybe a couple of different areas of mathematics, seeing some patterns and saying, oh, hey, these two patterns kind of fit together. Oh, cool. I can take two things and make something new. All right. So, I don't know that it's necessarily going to be humans that are going to be doing these next steps. Think of image generation, right? I mean, what do we have? We have a huge collection of images. They're labeled, they give a probability distribution, and now what happens when you generate new images? They are looking for places in the image space that hasn't been seen before. All right, and it AI it does it a pretty amazing job given the short amount of time that things like Dolly and stuff have been around
Yeah.
at generating new images. All
Yeah,
right.
it's got
So
really good really quickly.
okay, so think about that as mathematics. Fine. But at the end of the day, the space of images is absolutely enormous. And if you randomly pick a point in the space of images, it is completely boring because it's like going back to the 1960s television when you didn't get any reception,
Mhm.
right? We have to be the ones who decide what's interesting. And I think that is a huge burden if you have, millions and millions of images flashing past you because the computers will produce this very, very rapidly. And somehow we have to decide what is it that we as humans actually care about. And it can either be from, an intellectually pleasing perspective, or it can be from the perspective of something that's fundamentally important, right? And and I don't know about you, but typically when I'm confronted with a new mathematical idea, my reaction is this is nonsense. This is just a bunch of words, right? Um, Abstract ideas are really hard to digest. Uh, and so I go on the grounds, oh, this guy is a famous mathematician. He has a lot of respect. If he says this is important, maybe I should pay a little bit of attention and spend some time thinking about what's going on, right?
That's what drove Voivodsky to formalization. He realized that people weren't actually reading what he wrote anymore. They were just assuming it was brilliant because he got a
Right.
feel.
But if Voivodsky says do this, and some Joe, because we've all gotten our emails of somebody who's figured out the meaning of the universe and has sent us a 100-page manuscript and says read this and you'll be enlightened. Uh,
Yeah.
if I
You get
got
one
that
a
from
day now.
what? Pardon?
You get one a day.
Yes, right. So,
Do one
we
a month.
filter on what we pay attention to by some social hierarchy. Well, if this computer is doing it, we don't have that social hierarchy anymore, and that makes it harder.
Mhm.
And that means we have to even have a higher level of training, but I'm not sure what that training is, right? So I think that, it's we have to become better mathematicians in order to, in the long run, this is my prediction, we will have to be better mathematicians because we have to filter the gems out of the garbage, and there's going to be enormous amounts of garbage.
My guess would be that the more we get all this stuff coming online, the more important it will be to have in-person interactions. So the way
I
you
think
figure out garbage is you invite the person for a colloquium, and they're standing in front of you at the blackboard telling you what they, explaining to you the mathematics.
But the person is a machine now.
Well,
I mean,
the
it's like
person is the person who told the machine to do the thing, and somebody's directing a machine to do something.
let me give you another analogy, Alex. If you open up Instagram or anything like that, and you look at something, you have to decide whether what you're looking at is AI generated or it's something real, right? We're seeing this problem already from the news, and you know
And even if it's
that's
real,
where life gets
what
hard.
you're seeing was made by a machine.
Right. Right, right. It just becomes a much higher level of understanding that is going to become required of us. And
so.
I,
In MathLib, we wanted to say we want this, we don't want this, but then we couldn't say it. And as a result, the library just sort of grows organically. If people make contributions and people are prepared to review them, then the contributions, are deemed worthy of MathLib. And and that in some sense is not a particularly, I don't know, maybe it is it's a sort of a half decent way of deciding where we want the library to go. But it's sort of more random than I was expecting. It's difficult to the maintainers don't have a coherent idea about what's important.
But isn't that how all good things come into existence? Is that it's,
Maybe.
random people contributing whatever they think is the right thing to contribute now?
Yeah,
I mean,
maybe.
that's why we keep talking about, individuals led science, right? Is because, when if it's just a handful of people saying what has to get done, things go stale very fast. You really, I think this organic, lots of eyeballs, lots of different interests is what is needed for vitality. And I don't think that this is any different, you know.
Interesting. One of the things I've always loved about the Lean community is that there's a lot of very wise people in there that seem to know a lot about how to run a big mathematics library. Even if they're not mathematicians, they just know a lot about what makes a library great. And we've stuck to these principles and have made what seems to be a great library. And I think it's just because there's a whole bunch of people in this community that are incredibly smart. It's quite a nerdy piece of software, and I think it does attract smart people. And the fact that there's so many smart people around is, I think, one of the reasons that it's doing so well. But that was one of the things that appealed to me when I showed up. It's like, oh, look, there's Reed Barton. Like, he's memeable, isn't he? He need to get like 3 gold medals at the IMO. Oh, look, there's Leo DeMara. He won a prize. It's kind of crazy. There's Kim Morrison. Yeah. So smart people are definitely very helpful. Maybe they'll continue to play a role.
I have to run. Thanks for the talk.
Yeah, no, thanks for coming.
Let's thank Kevin again. Thank you so much.
Right.
Yeah, that was great. We really appreciate your time.
Yeah, no, thanks for the prime number theorem stuff. Uh, yeah, it'd be interesting to see what Gauss do next, huh?
Yeah, I mean, all of them. They're all running. When we talked about this in May, it was a complete pipe dream. And there's like 6 different companies that have an auto prover online.
Yeah, yeah, yeah. It's kind of crazy. 2025 is a crazy year. Maybe this year will be crazier.
Exactly.
I, I will stop using your time. I'll stop sharing.
I guess I'll see you at the Newton Institute.
You'll see me at the Newton Institute, if not before. Yeah.
All right.
Cheers.
Thanks,
Bye.
Kevin. All right.